Okay, so welcome back, everybody. Hope you're all doing well. Hope you're all staying safe and healthy out there. We're going to continue on with the recap of Physics 44. We kind of go in order through all the chapters that we covered this semester and highlight and summarize some of the most important points. We're going to continue with that, and where we left off was Chapter 4. So let's move on to Chapter 5. And the topic of Chapter 5 is applications of Newton's laws. So now that we know the basics, we know what the three laws of motion say, we know how to use them. If we want to take it a step further, what we need to talk about is what are some of the most common forces that we're going to encounter out there in the world and in problems. So, in other words, types of forces. Well, one really important force is what we call weight. And weight is just the force of gravity. It's a downward force. Downward force of gravity on an object. Okay, so the weight, vector W, has a magnitude equal to m times g, where g is equal to 9.8 meters per second squared near Earth's surface. Okay, so g can take on other values in other contexts, but weight is given by mg, and it's a downward force. Okay, so the next type of force that I want to review is normal forces. So normal forces are forces between surfaces that are in contact. And let's remember what the normal in normal force actually means. Normal means perpendicular. In particular, perpendicular to the surface. Okay, so we have a formula for the weight. What we don't have is a formula for the normal force, and that's because there is no formula. In other words, there's no sort of one-size-fits-all formula for the normal force. It actually depends on the situation. So to illustrate this point, I'm going to show you two examples. Okay, first one is something really simple where we have a box resting on a table, and that table is perfectly flat. So x direction is horizontal, y direction is vertical like this. If I draw a free body diagram of this box here, I'm going to see that the normal force from the table is going up, whereas the weight, the force of gravity acting on this thing, is going down. Okay, so if I apply F equals ma to the y direction for this box, okay, so the net force in the y direction is m times ay. Well, there are two forces, N and W. N is positive, W is negative because it's pointing down. And the acceleration in the y direction is 0 because this box is just resting there. It's not actually accelerating up or down. So that tells us that the normal force is equal to the weight, which is mg. But again, that's not just a formula you can always use, because in a different context, the normal force will be something else. So let me show you an example of that. Here, I have the same box. Let's try that again. The same box on a ramp. And the ramp is angled at some angle, we'll call it theta. So there's the box. And this time, I'm going to use a slightly different coordinate system just to work out the problem. X is going down the ramp. Y is going out of the ramp like this. And if I draw a force diagram of this box, well, the normal force now is going to be rotated. It's not going straight up. Remember, it's always perpendicular to the surface. It's going to be coming out of the ramp like this in the y direction. But the weight that hasn't changed. Force of gravity doesn't care if you're on a ramp, if you're on a flat surface, it's always going down. So there it is, there's W. So N is pointing directly along the y-axis, but W we can break into components. So this component is WY, it's going in the y direction. This component is WX, that's the x component. So what I can do is the same thing as before. The net force in the y direction is m times AY. And just like before, there is no acceleration in the y direction because it's not like the box is coming off the ramp or going down into the ramp. It's just moving along the surface of the ramp. It's only moving in the x direction. So yeah, we can say y acceleration is 0. But what does that actually give us for the normal force? We have N in the positive y direction. But then we have WY in the negative y direction. And I'm not going to go through the trig here. It works out to mg cos theta. Okay? And that's what's equal to 0. So in this context, the normal force is mg cos theta. Okay? So the point here is there's not some kind of one-size-fits-all formula that you can always use for the normal force. Okay? So the next one is tension. What is tension all about? Well, tension is a pulling force that's transmitted along the length of an object. And if you want to picture something, you can think of, let's say, a rope or a string, for example. So to kind of sketch that out, maybe you have a box and it's being pulled this way by a rope. There's some kind of tension in that rope. That's the idea. And just like before, there is no formula for this. Right? The tension depends on the context, okay? There's no ready-made formula to calculate T. It's kind of like the normal force in that way. Okay, so the next one is friction. This is another type of force that we need to get used to. So friction is a force that opposes sliding motion. Between two surfaces. And if you recall, there are actually two types, static and kinetic, that we need to think about. So when we have static friction, this is referring to the case where there's no motion or no relative motion between the surfaces. So let's say you're pushing a box, you're trying to get it to slide across the floor, but if you don't push it hard enough, it's not actually going to move. So in that case, the force that's opposing your push is called static friction. And the way it works is static friction is less than or equal to μs times n. This number mu is called a coefficient of friction. And it has to do with roughness and smoothness of the surfaces. Or I should say roughness or smoothness of the surfaces. So mu is equal to 0. That's perfectly smooth. That means we have no friction at all. And then bigger values of mu, like close to 1, let's say, are very rough. Okay? So that's what that coefficient of friction is telling you. Now, N is just the normal force. So apparently it's not just how rough or smooth the surfaces are that matters, it's also the normal force, which is telling you how hard the two surfaces are being pressed together. So all of this comes into play when it comes to friction. Okay, the other type of friction is called kinetic friction. And you can probably guess this is when there is relative motion, or there is sliding motion between the surfaces. Okay, in this case, we use Fk, and it's not given by an inequality. So the static friction force over here is less than or equal to mu s times n, and that means there is a maximum value for static friction. On the other hand, for kinetic, it's just equal to mu k times n, so it's a constant value. So in other words, static friction can increase in response to other applied forces up to some maximum. That's what the inequality is telling us. Kinetic friction is just equal to mu k times n. It's a constant force. Okay, so those are the different types of forces that I want us to think about. The next thing I want us to think about is circular motion. So let's say we have an object that moves in a circle at a constant speed. This object is accelerating. Okay, that's a really important point to make. And if you recall what acceleration is about, it's about changes in velocity. And in particular, we can calculate acceleration as delta v over delta t. Now, as long as velocity is changing, as time goes on, you have acceleration. So velocity can be changing in one of two ways. The magnitude can change, meaning you're speeding up or slowing down, or the direction can change. That's what's happening here when we move in a circle. The direction of velocity is constantly changing to kind of sketch this out. Let's say this is our circle. Oops. Right here. So let's say when the object is here on the right side of the circle, its velocity would be going straight up like this. But when it's on the top part of the circle, its velocity will be going to the left like this. And then when it's on the left side of the circle, its velocity will be going down like this. So you can see that the velocity direction is constantly changing, so we do have acceleration. Now, what can we say about this acceleration? Well, it has a name. It's called centripetal acceleration. And the reason we call it centripetal acceleration is because it points inwards. That is towards the center of the circle. Okay, so centripetal is a word that means center seeking. So if it points towards the center of the circle, we call it centripetal acceleration. The magnitude of this acceleration, okay, the magnitude of A is given by v squared divided by r, where v is the speed and r is the radius. That's what this equation is telling us. Okay? So to sketch out the picture, that's the circle we're moving in. It has a certain radius, distance from the center to the edge. And if I draw the object that's moving in that circle, let's say this is the object, okay, the acceleration is going to be pointing in towards the center of that circle. By the way, v is going to be pointing tangent to that circle. So A and v are at right angles. Okay? So that really covers it for chapter 5. This just outlines various applications of Newton's laws. We have different types of forces to think about. And we also have this idea of centripetal acceleration, which will come into play when we apply Newton's laws. Okay, so that takes us to the next chapter, which is chapter 6. And the topic is gravity. So we've seen a little bit about gravity, at least how it works when you're kind of close to Earth's surface. Talked about projectile motion and this idea that there's a force called weight. But to really dive into this, we need to talk about the law of universal gravitation that was developed by Newton. So this is Newton's law of universal gravitation. And what it does, it explains how gravity in general in the universe works. Okay? So as a statement, we have every particle in the universe attracts every other particle with a force called gravity. So in other words, gravity is not just something that big objects exert on small objects, okay? Any two objects in the universe that have mass are going to exert forces of gravity on each other. So that in that sense, it's universal. So what we want to do is think about just two random masses, m1 and m2, let's say. And let's say that they're separated by a distance, and we'll call that r. Okay, so the force is attractive, meaning mass number 1 is going to be feeling a force that's going towards mass number 2, and vice versa, right? Mass 2 is going to be feeling a force going towards mass 1. That's how I show they're attracting each other. So this force we can call F21. That's the force that 2 exerts on 1. And this other force is F12. And of course, according to Newton's third law, those are equal and opposite forces. But we're interested in how big the force is. Like, what is the force of attraction F12? And what's F21? Well, of course, they're the same in magnitude. But the formula is as follows. We have G, M1, M2, divided by r squared. Okay, so M1 and M2, those are the two masses, of course. R is the separation. This number G is what we call the universal gravitational constant. It's equal to 6.67, 10 to the minus 11. The units are newtons times meters squared per kilogram squared. Now, of course, you want to keep this separate from little g, which is the acceleration due to gravity. Big G is a universal constant, so anytime you calculate the force of gravity, use the same exact number. Doesn't matter what the two masses are. Any two masses in the universe follows this law. Okay, if we kind of take note about the form of the law, the force of gravity, we can say is proportional to, that's what that symbol means, 1 over r squared. So sometimes what we say is the force of gravity follows an inverse square law. Because it's the inverse of the square of the distance that gravity depends on. In other words, it's proportional to 1 over r squared. Okay, so one really useful way we can apply this now is for circular orbits. So I imagine that I have two masses, and one of them I'll call big M, and the other one I'll call little m. And the assumption here is the mass big M is much, much bigger than little m. Okay, so it's sort of the dominant mass of the system. To sketch a picture of what that looks like, that's going to be big M. Some kind of spherical object, could be a planet or a star or anything like that. And it has a certain radius to it. We'll call that big R. Okay, now somewhere in the vicinity of this dominant mass big M, we have little m. So we can imagine this is some kind of satellite that's orbiting around big M. Okay? So if we sort of sketch out that orbit like so, so this is the path that little m is going to take as it orbits big M. It's circular. And there's something we could say about that orbit. It has a certain height or altitude above the surface. So that's h. But keep in mind that what we actually care about is the radius of the orbit. So the radius of the orbit, I'm going to use lowercase r for that, is actually the distance from the center of big M out to where little m is located. So that would be the radius of the object plus the height above the object. That's what we're talking about when we talk about the radius of the orbit. Okay, so what we can do is apply F equals ma. In this case, we're not going to do it for the x or the y direction. We're going to do it for the radial direction. And the idea here is if a force is going in towards the center, that will be positive. And if the force is going out away from the center, that would be considered negative. So actually, I'm going to draw M again down here just to show that the force is attractive and it's going towards big M. There's the force of gravity acting on little m. It's going inwards. Okay, so because that force is going inwards, we'll give it a positive sign. And we know now that the force is given by G, big M, little m. Those are the two masses, divided by r squared, that's the radius. And that equals m times a. But also remember that the acceleration for something moving in a circle at a constant speed is v squared divided by r. So we can cancel out little m. That actually doesn't matter. We can also cancel out one factor of r. And what we get is v, that's our orbital speed, is the square root of big G, big M divided by the orbital radius. So this is our orbital speed. Okay, there's actually another way we can think about the orbital speed. It's the distance we travel divided by the time it takes us to travel that distance. If we're talking about a circular orbit, well, the distance is 2 pi r. And the time, I'm going to call that capital T, that's what we call the period of the orbit. So the period is the time to make one full revolution, one full orbit. So again, if we think of speed as being distance over time, the distance we travel is the circumference, so that's 2 pi r, that's the formula for circumference, divided by the period. So if we wanted to, we could use this to, let's say, calculate the period. Okay, so the last topic in chapter 6 that I want to go over is acceleration due to gravity. And as a variable, we're used to seeing this as lowercase g, so not to be confused with uppercase g. Lowercase g is the acceleration due to gravity. And the general picture that you should have in mind is this. We have some kind of, again, dominant mass, big M. And think of it as some kind of spherical object like a planet or a star. And in the vicinity of that massive object, we have a little object, lowercase m. And of course, lowercase m is going to be feeling a force, an attractive force of gravity towards the big mass. Okay? So the assumption that we're going to make here is that the height off of the surface of the big object is small compared to the radius of that big object. And if you think about it, this is pretty much always the case for any one of us as we go about our day. You may, walk up the stairs and go to the second floor of a building. That height that you gain in doing that is just absolutely tiny compared to the radius of the Earth. Even if you go to the top of Mount Everest, it's actually still the case that the height off the surface of the Earth is still really tiny compared to the radius. So for that reason, we can think of r, lowercase r, which is your distance from the center, as being basically the same as the radius of the object, even if you change your altitude slightly as you go about your day, right? It's pretty much always the case that your distance from the center is basically just the radius of the Earth. So there we go. Now, if we apply F equals ma to this object, well, here's what that will give us. Let's, for now, just think in terms of magnitudes, okay? The magnitude of this force of gravity is G, big M, little m, divided by r squared. And on the other side of the equation, I just have mass times acceleration. Now, what we call this acceleration is g. So instead of ma, I'm just going to write mg because little g is just a special type of acceleration. And what we'll do next is simply cancel out little m. And that gives us little g is equal to big G, big M divided by r squared. Okay, so for instance, if you were to plug in the mass, that's big M, in the radius, that's big R, of Earth, here's what you'd get. 9.8 meters per second squared. So that's actually where that number we've seen before comes from. Okay? So that's pretty much everything I wanted to talk about for chapter 6. Let's move on to the next one. All right. So last chapter to go through is chapter 9. So remember, we skipped over 7 and 8. We're actually going to go through those in Physics 45. So for now, we're just going to skip ahead to momentum. And there's a lot to say here in chapter 9. So the first thing is just to define some basic terms. When we use the word momentum, conceptually, you can think of momentum as being a measure of how difficult it would be to bring a moving object to a stop. Okay, so in other words, if an object has a lot of momentum, it's very difficult to bring it to a stop in some sense. And if an object has very low momentum, then it's quite easy to bring it to a stop. But now we need to get a little bit more precise than that. The formula for momentum is m times v. So momentum is given by lowercase p. It's equal to mass times velocity, and it is a vector quantity. So the direction absolutely matters for momentum. So one reason that momentum is important is it relates to force. So there's a relationship between force and momentum. And this can be written in a lot of different ways, but what we're familiar with is saying delta P is equal to F average times delta T. Okay, so let's start off with an example. Let's say we have a ball bouncing off the floor. Okay, so the ball comes in moving something like this. It hits the floor. And then after it hits the floor, it's moving off in another direction. Okay, so the momentum initial is right there. That's P initial. That is the momentum before it hit the floor. This would be P final, the momentum of our ball after it hit the floor. And of course, delta P, any sort of delta is a change or the difference between final and initial. So this would be P final minus P initial. Okay? All right, so in our equation, we have delta P is equal to the average force times delta T. Okay, so this is saying that if we have a change in momentum, that equals the force involved times the time that that force acted for. Okay, so if we want to get a change in momentum, a force needs to be exerted for some amount of time. That's really what this is saying. And for this example, I want us to get some sense of what that force looks like. So I'm going to draw a diagram. When we have P final minus P initial, this can be thought of as P final plus negative P initial. And right here, what's being described is vector addition. Okay, I'm adding two vectors to get delta P. So let's do that. I can use the tip to tail method to add these two vectors. And I'm going to start by drawing P final. P final points kind of up into the right like this. So there's P final. Now P initial points down into the right like this. But what I want to do is add negative P initial, which points in the exact opposite direction. So here's negative P initial. And those are connected tip to tail. So P final plus negative P initial, that's what it looks like. The resultant vector is delta P. So that's going to be pointing straight up, again, from the start of P final to the end of negative P initial. So delta P is pointing straight up, and this is telling us something. Okay, this is telling us the force that the floor exerts on the ball is straight up. And if I wanted to put a number to it, of course I could calculate it using this equation. Okay? But that's the idea. There's some kind of force involved in this bounce. It's very closely related to the change in momentum. Okay, and that leads us to the next topic, which is conservation of momentum. So what is this all about? Well, the law of conservation of momentum says if there is no external force acting on a system, there we go, the momentum of that system will be conserved. And in this case, when we say conserved, we just mean it's not changing over time, okay? So the momentum is just a constant. It has the same value regardless of when we're looking at the system. So to put this in a more compact way, what we can say is if we have a system where the net external force, that's take all the outside forces, add them together, that's what we mean by external. If we get 0, then we can conclusively say that the momentum of that system, P, is conserved. And the way we usually think about this is P initial is equal to P final. So if we look at the system at some initial moment in time, and then we look at the system sometime later at some final moment in time, we're going to have the same momentum. Now, the most common use of this is in a two-body collision, or the most common that we've seen at least, is in a two-body collision where you have two objects, let's call them A and B, which are moving in some kind of way, some velocity, let's call it VA, and some other velocity, let's call it VB. And as we can see, they're approaching each other, so they're going to collide, but this is before that happens, before collision. Okay, after they collide, they're going to be moving with some new velocities. So maybe like this. This is what we'll call VA prime, and this is what we'll call VB prime. And this is the after collision picture. what conservation of momentum allows us to do is relate what's going on before collision to what's going on after collision. So if P initial is equal to P final for this system, okay, and that means we have to account for both objects, here's what this tells us. MA times VA, okay, that would be the initial momentum of object A, plus MB times VB, that would be the initial momentum of object B, is going to equal MA VA prime, that's the final momentum for object A, plus MB VB prime. That's conservation of momentum in a two-body collision. That's how it works. Okay, so to say a little bit more about collisions, there's more than one way a collision can happen. So in particular, we have what are called elastic and inelastic collisions. And before we define that, let's review kinetic energy. And kinetic energy is the energy associated with motion. Okay, so an object has kinetic energy just by virtue of the way it's moving around. So we can calculate kinetic energy, K, as 1/2 mv squared. And of course, m is the mass and v is the speed here. So it's not velocity, it's speed. Okay, and that tells us that this is a scalar quantity. It doesn't have a direction associated with it. All right, so this brings us to the two types of collisions, elastic, or an elastic collision. That's a collision where the total kinetic energy of the colliding objects so the total kinetic energy of the colliding objects is conserved. So they have just as much kinetic energy before they hit as after they hit. So what we can say is K initial is equal to K final, but make sure that when you actually use this idea, you're accounting for the kinetic energy of both objects. We're talking about the total kinetic energy. And in the case of inelastic collisions, we have some amount of kinetic energy that's lost. Okay, so we don't have the exact same amount before and after. So the initial kinetic energy is actually greater than the final. Okay, so one thing that we know about energy is that it's a conserved quantity. So it's not as if, the energy that's lost in this collision just disappears. It just gets transformed to other types of energy. So it's converted to things like sound or heat or deformation of the objects. Okay, so those are just some places that this lost kinetic energy can go in an inelastic collision. Okay, so some sound might be produced. Okay, you can hear the collision. Heat, meaning the temperature of the colliding objects, can be raised, and the objects will be deformed in some way. Maybe they'll break or fracture or compress in some way. This is all just different places the energy could be going in an inelastic collision. Next topic, center of mass. So let's write the definition down first. The center of mass of a system, we can think of that as the average position. Okay, it's the average position of the mass in that system. Okay, so we need to kind of narrow that down. That's the rough idea. But in particular, if we look at this example of a system of three masses, let's say M1 is right there, M2 is right here, M3 is down here. Let's draw a coordinate system so we can keep track of where everything is. So X and Y like this. The center of mass is the average position of those three masses. Well, we somewhat expect it to be, in the middle somewhere. So let's just write that X is where the center of mass is. But I want some way of actually calculating what that point called the center of mass is, where it's located. So this is RCM. This is the position of the center of mass. The way we calculate RCM, so the position of the center of mass, or CM for short, is given by 1 divided by big M, that's the total mass right there, times sum from I equals 1 to N of M sub I times R sub I. Okay, so this is one of the masses. We use little m. And when we say R sub I, we're talking about the position of that mass. Okay, so that's how we write it in sort of a compact summation notation. If we expand that out, really what's happening is on the top, we have M1 times R1 plus M2 times R2 plus M3 times R3. You can kind of see the pattern here. On the bottom, we have big M, that's the total mass. So that's just M1 plus M2 plus M3 and so on. So that's the way we're taking the average position, okay? And so this is what we call a weighted average in the sense that the bigger the mass is, the closer the center of mass is going to be to that object, okay? So if M1 is much, much bigger than all of the others, then the center of mass is going to be really close to M1, okay? If M3 is much bigger than all of the others, then the center of mass is going to be really close to M3. Okay, so the last thing to say is the center of mass, of course, is a position. So we can talk about the x-coordinate, xcm, and we can talk about the y-coordinate, ycm. And of course, the only thing that really changes when we calculate those coordinates is instead of r, which is a vector, we have just x. So 1 over the total mass from I equals 1 to n, that sum of mi xi. In the same way, if I wanted the y-coordinate of the center of mass, it would be 1 over the total mass times the sum I equals 1 to n of mi yi. So that's typically how we actually use this, is we kind of go by component, sort of look at x and y separately, and that's how it works. Okay, so why does the center of mass actually matter? Well, it's actually a really important concept in physics, and as you go into Physics 45, you'll see this come up a lot more. But one way that we see this comes up is in Newton's second law for a system of particles. Okay, so what we have up here with these three masses, M1, M2, M3, that's an example of a system of particles. And here's how it goes. If we take the net external force, so sum up all the external forces, that's going to equal big M, again, that's the total mass of the system, times ACM. Okay, so if we kind of put this in words, it's the net external force, or outside force, that acts on a system. That's going to determine how the center of mass moves. So the net external force acting on a system determines how the center of mass moves. That's the basic idea behind this. So the center of mass is playing an important role, as I said. So let's take a look at an example. Okay, an object, a spinning object, launched into the air. Okay, so let's say our object is this thing right here, just kind of like a wooden plank. The center of mass is right there in the middle somewhere. And we have the force of gravity, or the weight, acting on that object. Now, this is the only external force. So gravity is the only external force. Of course, if we ignore air resistance, ignore air resistance. There we go. And so if we apply this idea that the net external force is equal to m times ACM, it gives us a really simple answer. So on the left side where we have external force, I'm really just going to write the force of gravity. And we know something about the force of gravity. Its magnitude is m times g. But if I want to show that it's going down, I would put a negative sign and then the j hat unit vector to say we're going in the negative y direction. Okay? And then on the other side, we just have m times ACM. Okay, well, the mass of this object obviously is just dropping out. And then what we get is ACM is equal to minus g times j hat. Well, we already know exactly what happens when an object has an acceleration of g in the negative y direction going downwards. It moves just like a projectile. Okay, so the center of mass in this case is going to move just like a projectile. So let's actually just draw that path. Projectiles move in these sort of parabolic paths like this. And so that's telling us that the center of mass of the object is following that path. Okay? But the rest of the object is spinning around like this. Okay? So the center of mass moves along this simple trajectory. And while it's doing that, the object rotates around that center of mass. Okay, so that's just one example of how we can sort of apply this idea. All right, and so with that said, that really concludes the Physics 44 course recap. We've gone through all the chapters that we've covered this semester. We've highlighted most of the important points that you're going to need to know and really study going into the final. Speaking of studying for the final, I have a review packet that I've posted. It has a bunch of problems that you can use to study, to practice for the upcoming final exam. So really go through those in addition to going through these videos. And just generally, I'd like to say good luck on your finals. Hope everything goes well. I know this is kind of a weird, unprecedented time that we're living in, but I hope you can make the most of it. I'm really looking forward to the time when we can all come back to campus and have classes face-to-face. It won't be too long, so just hang in there. And in the meantime, again, just try to make the most of what we have here with the online classes. So to kind of wrap things up here, I'd just like to say it's been a pleasure to get to know all of you. I hope you had fun this semester, and have a nice summer. I'll see you next time. Take care.